Okay, are we good?
Thank you, Mark.
Great, yeah, so I'm going to give an overview of the technique, and I've kind of provisionally entitled this The Art of Mineral Exploration, because as you'll see, a lot of these data sets that we're going to discuss today are actually extremely beautiful images and contain a lot of data. So primarily the data sets that we're going to discuss today are micro XRF maps, and they come from an instrument called the Maia mapper. So firstly, I'm going to talk a bit about the Maia mapper. What is it? Why do we use it? Why do we think it's such a great tool for investigating mineral deposits? And then I'll talk through a couple of case studies, and the other speakers, Sam, Shirley, and Steve, will all give examples from different types of ore deposits. So the kind of reason behind developing this technique was that a lot of the research we do as scientists is on small scale data sets. So on the left here, you can see we've got some thin sections. There's an automated mineralogy map. There's some electron backscatter diffraction data and some nanosims. And the scale of these data sets is kind of nanometers up to hundreds of microns. Industry data sets that these complement typically are focused at the core scale to deposit scale and even to kind of camp and regional scales. So there's a bit of a gap between this core scale shown on the right and the microscale research data. And so we wanted an instrument that filled this gap. So we developed a micro XRF, X-ray fluorescence instrument that does exactly that. And the challenge set to our team was scanning 50 centimeter lengths of HQ core with 30 micron resolution. And this links us then to techniques like laser ablation and SIMS, and with quantitative analysis of trace elements down at a few tens of ppm level. And the solution includes a Maia detector, which is an array X-ray detector that was originally developed by CSIRO and Brookhaven National Lab in the US for synchrotron experiments. And we took this and brought it into the lab in this lab scale instrument, picture of which you can see on the right. The X-rays are provided by an Exelum liquid metal microfocus source, which is a relatively new development and has a much higher X-ray flux than conventional X-ray tubes, allowing us to map these large samples in reasonable timeframes. And we made use of new X-ray lenses that are developed for relatively high energy X-ray applications in the lab. So what does this look like inside? If we open up the box, you can see the X-ray source at the back, the detector, where the X-ray beam is threaded through this central window, and the X-ray beam comes through, hits the sample, which is mounted vertically. This is a piece of half core, and moves backwards and forwards in front of the X-ray beam, and the X-rays are collected in a backscatter geometry. And we can map samples of half core with timescales on the order of a day or so for the sample to get that high definition image. So in terms of accessing the Maia mapper, we typically incorporate this as part of a workflow where we take core scale data sets and link it using the Maia mapper to microscale analyses to solve particular problems that have been posed to us in terms of ore genesis or understanding the geometallurgy of ore deposits. But we also have some ability to run these as separate samples, and in general we charge on the order of $1,750 a sample for typical acquisition conditions. We can produce a single matrix data set because we have to state the mineral matrix that we need in order to process the data. And we can output red, green, blue, and elemental concentration images relatively easily. And we have a web viewer in development for this technique. And if you want any more details, then my address is at the bottom there. Let's show you a few examples of data sets that have been produced with this instrument and the kind of results that we can start to look at. So the first example comes from the Abra polymetallic lead, zinc, silver deposit. There's a whole bunch of other elements, copper and gold in there as well. And this is it's a relatively enigmatic deposit in the Capricorn origin. And the piece of core that I'm going to talk about is it's shown at the top there. It's just an optical image, and you can see this banded structure to the core. With iron oxides and carbonate layers. And the first thing we can do is have a look at where the economic elements of interest sit. So the first image in the middle is a copper, zinc, lead map, and these are shown in red, green, and blue respectively. And this is how all these maps are going to be shown. So the beauty of these data sets is we have the context of the piece of core. So we're imaging a whole, in this case, 23 centimeter piece of core. But we also have the detail that these maps provide. So we can zoom into these. We can zoom into these maps here and have a look at the kind of microscale situation of these elements. So if we look at where the lead in blue, for example, is, we can see it definitely occurs in the center of these carbonate regions, and there's carbonate that's grown outside of these. We can also look at the copper in red, which is within these coliform banded layers at the top. Because we're imaging such a large volume, we can start collecting statistics on where these different elements sit. So we could take each of the lead-rich regions and we can look at the elements around it and collect a kind of neighborhood of what that chemical environment is and start doing statistical analyses on these so that we're actually able to confirm what's representative of particular elements in minerals. And that's one of the big advantages of these data sets, is that we can actually look, before we do that microscale analysis, at the representativity of what we're analyzing. If we look at the same area but change the elements in the image, we now have iron in red, manganese in green, and zinc in blue, and we can see it looks very different. We can still see the coliform structures, and the blue of the zinc is picking out these coliform structures here. And the manganese in green is picking out very nicely the vein carbonates. Where we have iron and zinc both hosted within the carbonates, this produces this kind of fuchsia layer. And this is telling us about when the zinc is arriving in the rock relative to when the carbonate grows. And the interesting thing about these microstructures is that the conventional model for the Abra deposit is one of kind of exhalative deposit, whereby the deposit is built up layer by layer. And the coliform microstructures that host the zinc kind of suggest that are consistent with this, suggest this is the case. However, if we look at the carbonate layers, we can see that these are growing from both sides of the veins into fill the gaps. So there's been a lot of dissolution and a lot of space filling within this rock. Oops. If we take a look at another part of this rock here, the black is where none of the elements that we're projecting is actually occur, and this is quartz, and you can see nice euhedral quartz grains here. And so these are growing off these iron oxide layers, again, on both the up core side and down core side at the same time. So we've not got this simple monotonous growth sequence of these minerals. We've got evidence for significant dissolution of these rocks and later replacement, where we have first quartz growing, and then these are overgrown by carbonates of various compositions. One final part of this image kind of shows that in a bit more detail, that we have this process going on throughout this length core. Again, we've got the euhedral quartz overgrown by various carbonates. So the history of this rock is a lot more complex than simply a banded exhalative sequence. My second example is from the Ernest IOCG deposit in Queensland. And this example again is we're asking questions about representativity. So microanalysis of pyrite, specifically with laser ablation, has produced some significant advancements in understanding gold and sulfides in mineral deposits over the last 10 years. But the technique's kind of time limited due to stability of instruments and cost. And so we can generally only analyze a few pyrite grains in each sample. So the question is, which ones do we analyze in order for it to be representative? So using these maps as a first pass, we're able to see some of the detail that we'll be able to later see with the laser, but without necessarily the analytical precision that we get with that instrument. So these techniques are very complementary to each other. So if we look at this first image, which is, again, this is a 16 centimeter piece of core. We're looking at cobalt in red, arsenic in green, and iron in yellow. Importantly, in this image, where cobalt and arsenic occur together, they mix to, iron in blue. Where cobalt and arsenic mix together, they form yellow. So that's something to bear in mind. If we zoom into this end of the core here, we can see that these relatively large pyrites have quite a complex growth history, and they have cobalt and arsenic rich cores, which is the really bright yellow stuff. And then as they grow outwards nice euhedrally, we get this kind of transition through yellow into this red layer, which is just a more cobalt rich. We lose the arsenic as the pyrite grows. We then have what looks like a period of dissolution. You can see that particularly on this grain here, where we have embayments forming in this yellow to kind of reddish material, and then that's subsequently overgrown by another generation of the pyrite. We can also see much smaller pyrites in here, and the iron oxides of in the bright blue color. So these rocks have experienced a magnetite flooding, and we can start to see when that occurs with respect to different generations of pyrite, because we're limited, the magnetite is limited to the very outside zones of the pyrite. For example, this one, this magnetite grade, here we can see that the abuts the corroded edge of this pyrite. If we look at a different part of the same sample, you can see that a lot of these pyrites here actually lack the bright yellow cores that the first lot. It was quite striking in the first lot of pyrite. And so we've got growth in different parts of the sample at different times as the chemistry evolves. These pyrites also have a more well-developed kind of generation of different composition after this red material was grown, and it's kind of this sort of reddy orange color that occurs before the low cobalt overgrowth. There's also a generation of much finer grained pyrite in here, which lacks any of that, any of those kind of core cobalt and arsenic bearing phases. And so we have nucleation and growth of pyrite over a protracted sequence of events as the chemistry of the rock is changing. And this allows us to be able to choose the pyrites that we want to in order to get a good representation. Just finally, if we look at the same image, but now we're looking at nickel in red and cobalt in green. Again, we can see the cobalt-rich parts that make up the large amount of the pyrite, but we can also see that the overgrowth that follows the dissolution of these early formed pyrites is actually nickel bearing. And we have a nickel bearing phase in the matrix as well, which is probably a chlorite. And so we can look at the distribution of these elements between different phases, not just limited to one particular phase. Again, if we look at this other generation that lacked the cobalt-rich cores, cobalt and arsenic-rich cores, we can see that later generation is nickel-bearing. So I hope that gives you a nice overview of some of the things we can look at with this technique, and I'll pass to I think Sam, who's going to talk a bit more about some sediment-hosted deposits.
Thanks, Mark. Can you hear me?
Yep. Excellent.
Okay, so I'm going to give some examples from the MacArthur River zinc lead silver deposit in Northern Australia. One of the key aspects of the research questions around when we worked at HYC of MacArthur River over the last few years is the questions remain over the syn sedimentary or exhalative SEDEX formation mechanisms versus an epigenetic formation mechanism, which can be of importance when exploring for these types of deposits. And I'll be exploring some different aspects of the ore material in terms of textural criteria and also trace element deportment, which the Maia mapper is very, very good at picking up. So this is just a very quick overview of the deposit in terms of its spatial variation, and this is these are contours of the pit. It's an open pit deposit. And in the central area, we have laminated sulfide textures, which is this image that we see here. We see these typical soft sediment deformation features and some minor fractures as the sediment is shifted around during deposition. And we have laminated sphalerite and galena textures through here, interbedded with pyrite and carbonaceous silt. Around the margins of the central zone, we have a much more laminated and modular carbonate texture. So this is typically what you see in these zones here, where we have crust form carbonate interbedded with carbonaceous and pyritic silt, with in places some brecciated carbonate textures. In this case, we've got a bit of imbricated fabric, and the base metal sulfides have precipitated around the margins and the center of these. So that's a zoom in of this nodular brecciated sample. If we then look at an RGB map of that, looking at iron in red, which in this case is pyrite, zinc in green, and calcium in blue, what we see is very, very clearly the zinc and the sphalerite is almost exclusively associated with spatially associated with being within the margins of dissolution textures within the carbonate. If we then look a little bit closer in here, I'm just going to pop out of PowerPoint for a second, get closer in. If we look at some of these textures in more detail, See, there's little bits of pyrite that occurs within the sphalerite, and if we just move around, we see in places that the pyrite has acted very, very fluid-like and is in places enveloped these sphaleritic carbonate nodules. So this could be interpreted as pyrite precipitating after, but when we look at this more closely on a micro scale, we can see that actually the pyrite has actually come before and the sphalerite has grown around it. If we look further down where the non-brecciated layers are, you can see there's absolutely no sphalerite through these zones at all. So this is in carbonaceous silt and interbedded pyrite carbonaceous silt. And you only get these tiny minor little blebs of sphalerite occurring. When we look at those in thin section in the micron scale, you can see that they too are actually surrounded by, and those two are actually replacing the carbonate just in a very, very small scale. So this is good evidence for carbonate replacement model in this fascies, whereby the fluids have come in, they've dissolved the carbonate, and sphalerite is precipitated at the site of that dissolution. Go back into PowerPoint now. Look at another example of this fascies where we can look at some trace element evidence for this type of mineral system. This is from the same section of the deposit, just a different ore lens. And what we see here is a laminated pyrite carbonaceous silt bed, which is being folded over, so a full slump feature, where we have laminated pyrite that's draping over nodular carbonate leads, which are sometimes continuous, sometimes not. If we then switch on the RGB Maia map, the same color scale as before, we can see that the same observations are made here, where we have sphalerite that occurs exclusively within the carbonate, and almost none of it at all occurs in these laminated sim depositional layers. Again, just going to jump out of PowerPoint and these in a bit more detail. See down here, if you look at some of these drape features, see that even in the smallest parts of nodular dolomite, have very, very close spatial association between sphalerite and carbonate, and almost none at all throughout this zone. There are little bits of zinc being picked up here, but nothing compared to what we see through here. Now, in this sample, what I want you to draw your attention to is this red zone, which occurs in between the sphaleritic carbonate nodules that have all been a bit brecciated in this folded zone. Everything's kind of broken up, and this is all laminated carbonaceous silt, which is a little bit lower grade. So it's in this area through here that I want to draw your attention to. Jump back into PowerPoint. What we're looking at here now is a quantitative heat map of thallium concentrations in the same sample. So thallium has been known about in McArthur River and other sediment-hosted zinc lead deposits for a long time, but very little is known about it. And one of the reasons it's poorly understood is because thallium is very difficult to measure using traditional lab-based X-ray techniques. But the Maia mapper, because of its high-powered X-rays and the Maia detector, is able to pick that up. So what we see here is that thallium is particularly concentrated in this zone through here in this Z-shaped fold. And this allows us to target specific areas if we want to do more detailed quantitative work, if we have questions around, for example, thallium. So what we're able to do is then focus on this area here and do a little bit more of this detailed micron or nanoscale work. So what we see in this area here is the pyrites formed of these central earlier cores, which are then overgrown by layers of euhedral later pyrite, and this all occurs paragenetically before the arrival of the base metal sulfides. So this is sphalerite through this bright zone here. And if we do some TOF sims, which is a nanoscale quantitative analytical technique, we can measure thallium in that field of view in this box here, and we see that thallium is almost exclusively associated with these late-stage overgrowths. So that can tell us an awful lot about the chemistry of the fluids that formed this ore deposit and the timing of that. One last quick example of this splash is at the McArthur River. This is another crust form, low to medium grade zinc sample here, where we see very, very typical carbonate replacement textures throughout the bedded carbonate. But what I want to draw your attention to is some of these vertical or subvertical fractures which occur throughout the bedded carbonate. If we look more closely at some of these, you can see that throughout these bedded carbonates, the sphalerite occurs always within the solution margins of those. But what I want to draw your attention to in these subvertical fractures is that some places the fractures cross-cut the carbonate, but they don't transect the pyrite lamin. So that suggests that the carbonate is being rigid during the deformation, but the carbonaceous and pyritic siltstone has remained quite plastic. Jump back into PowerPoint very quickly. What I want to highlight here is the occurrence of copper in this ore deposit. Copper is poorly understood and not very well documented in these types of zinc-lead deposits. But what we have here is zinc's now gone to red, we've got lead in green, and the copper's in blue. And if you just let me jump back out of PowerPoint, and we can look in more detail, what we see in these areas here is that we've got the usual carbonate associated sphalerite, which in this case is red, but the subvertical and vertical fractures are actually purple. So this is copper bearing sphalerite with some localized blue through here. So that's more often than not chalcopyrite through here. So what we have in this sample in particular is two different end members of sphalerite, copper rich and copper, which occurs throughout the ore zone. And one last final sample I want to show you is one of the laminated soft sediment deformation batches samples. This is what we covered. This is a very high grade sample with no dolomite left over to speak of. What I want to take into is that area here. Just go in. What we see is this batches. This is a really, really pretty rock, but it's so high grade it doesn't have to tell us much, because any carbonate that was there, if our model is correct, carbonate replacement, if that's correct, all the carbonate in this species is completely gone and being replaced by sphalerite. But the textures of the original carbonate are preserved. So what we see through here is these really nice soft growth faults which occur through this laminated bed. We've got a fining upward sequence of siliciclastics through here with some calcium bearing phases. And then if you look at this fracture through here, which in places is filled with calcite, it comes up through here and it hits this soft fold through here. It kind of disturbs the hinge a little bit through here, but doesn't actually displace the beds, but then it kicks off back through here. And this type of sample that's so high grade doesn't actually tell us too much about the formation, but they're certainly extremely pretty. So I'm going to now pass on to my colleague Shirley, who I think is going to talk about some hydrothermal deposits. Seafloor.
Could you stop sharing? Okay, yeah, you stopped. Okay. Okay, everyone can see my slides. Hello, everyone. Thanks for Mark and Sam for the good introduction about my mapper and the beautiful image from the samples. And now welcome to the deep sea world. And I think most of can you see the video?
Yeah, you can see it.
Yeah, just stop frozen for a while. Sorry. I think most of you must have been familiar with this video. So they are deep sea venting fluid. They're also called black smokers, as they keep discharging the black fluid into the ocean. So they're enriched in sulfides and contain a lot of the metals like copper, zinc, gold, and silver. So as one of the extreme environment on Earth, they are unique habitats hosting a wide range of the micro and macro organisms. More importantly, they are modern analog of ancient VMS products. These samples are very precious because very difficult and expensive to find them. So the study about the texture and the growth history of the chimneys still like need more study. So by studying the chimneys, it can provide valuable information for us to understand the forming process of modern worlds. So because the samples are precious, so before we crush them into powder, it's very good to use Maia mapper to investigate the distribution of the trace metals and to understand the textures and growth history. So the first example is a copper zinc rich chimney. And this is a photo of hand specimen. So from here we can see the distribution of chalcopyrite and it forms the wall of the conduit where the fluid passing by here, and also overgrown by sphalerite. So this is the information we can get from the chimneys. If you look at the map, it's a copper arsenic iron map. So the pink is the chalcopyrite and blue is pyrite. So we can see the chalcopyrite is dominated by the coarse grains, and we can see the individual chalcopyrite grows towards the fluid conduits. This represents the precipitate from a relatively saturated conditions, where the hot damping fluid slowly mixed with a small amount of seawater. Also, we can observe that there's a lot of fine-grained chalcopyrite. They form the fine-grained particles or form as dendritic structures grows away from the conduits. They are precipitated from the supersaturated condition, where the venting fluid are quickly mixing with the cold seawater. And this chalcopyrite overgrows separate with existing pyrite here. So here we identify the pyrite as the stage 1, like an early stage, but probably precipitated from another early hydrothermal fluid, and the chalcopyrite is stage 2 here. And also we can see that the boundaries between the coarse grain and fine grain studies. I want to zoom in the image here within the time limit, but I will tell you that we also did a similar study on the thin section scale of these samples, and we found these boundaries is enriched in sphalerite, gold, and micro scale native gold and some pyrite, and that represents the primary wall and the initial fluid mixing happened here. So from this simple map, we can get a lot of information when it comes from the hand specimen with the naked eyes. So the information we can get includes that this region actually involves the different degrees of mixing between the venting fluid and seawater. And also we can see how the venting fluid diffused into the space out of the wall when it initially formed. Then we have the later stage sphalerite overgrows the fine-grained chalcopyrite here. If we take a look at the arsenic zinc and the barium distribution here, so we can see the outer part of the chimneys is dominated by the sphalerite in green and the barite in blue. And also some lead-rich minerals occurs in the voids and minerals. So our later petrographic study showed that arsenic we co-located the slat to form the lead arsenic surface here. So the overgrowth minerals represent a later stage when the venting fluid mixed extensively with the seawater here. Also, we have another new recent study to look at the lead arsenic surface here. They form these filament structures here, and they are strongly associated with the arsenic-related microbial activity. So, if you have an interest to look at this paper, and it shows how the microbial strategy in living in such a highly toxic, acidic, and acid warm environment here. Okay, so the second example is a sphalerite chimney. So the right is the bottom is on the right and the left at the top. I didn't have the original photo of the chimney, so I used a grayscale image here. If we take a look at the copper zinc iron, so we can see basically the chimney is dominated by sphalerite here, and with some pyrite and chalk pyrite associated to the copper, to the bottom. So here in this one, the chalk pyrite it doesn't form the fluid contour as you have observed. Instead, you can see some copper sulfur. They form a replacement of some microbes here, and some over here. You can observe that. If we zoom in part of the sphalerite, we can see which is a sphalerite form with linear branching dendritic structure here goes from center to the outer part of the chimneys. This shows that the most of the chimney are prefixed from a relatively quick mixing of the fluid. So what information we can get from this map? Because we all know that sphalerite is a relatively low temperature mineral. So this chimney are supposed to form from a relative low temperature venting fluid, and also happened during the quick mixing between the low temperature fluid mixed with the seawater here. Also, the strontium and the barren distribution can give us a good idea of how the seawater interacts with the chimney, because they can show very strong seawater signatures. So we can see the strontium and the barren is usually formed as barite. They only occurs on the boundaries of the chimneys, and some will infiltrate into the center. This shows how the seawater is infiltrated into the chimneys. So it only stopped here and didn't go any further. If you look at the arsenic and the barite, arsenic still shows a similar distribution with the previous one, and it occurs as the lead arsenic sulfur salt within the voids of the minerals, and also they contribute to the replacement of bioorganisms. So here I just showed two studies of the different chimneys, how the variation of the distribution of metals here. How can it apply to the VMS exploration? So we know there's different type of chimneys that have different enrichment of metals and associated with different hydrothermal activities. So, and this is a kind of response to the different positions in the Seafloor hydrothermal system. So this primary texture can be compared with the sulfide samples in your VMS forward, and further will give you imputation to show the possible original positions of the sulfide in the original Seafloor hydrothermal system. And also the texture and structure, they are very primary, as they haven't suffered any metamorphism, hydrothermal alteration, or segmentation. So if you find your sample is very complicated, as Sam and Mark shows in their samples, so our texture can give you a very good understanding about what are the secondary processes that happened after the formation of the formation groups. Okay, and that's the end of it, and thank you, and I will pass it to Steve. Steve?
Right. Hello. Yes, I'm here. Good. I'm just finding my unmute button. Can everybody hear me?
Yeah.
Okay, good. So I just need to find the right screen to share, and we are good. Right, with you. Share content. PowerPoint up. Oh, now I've lost it. Hold on. Share content. I think that's the one. Okay, now you should see you should be seeing a full PowerPoint screen now. Oh, right. Okay. Good. So, right, I'm going to talk a little bit about some work I've been doing with some colleagues on the Morensky Reef. And the Morensky Reef is a remarkable body of rock. It's up until a few years ago, it was the source of almost all of the world's platinum group metals. There are a few rivals now, but it's still a very important producer. The Morensky Reef is a remarkable body of rock. It's a stratiform layer. You're looking at the whole thing in these two images here. A photograph of a polished slab on the left and a Maia image of a different polished slab on the right. That's the entire Morensky Reef you're looking at in both of those images. It's in that case only a few centimeters thick. Typically goes up to about 20 centimeters thick, sometimes a bit more. And it's continuous for 400 kilometers. That's 400 kilometers across the entire width of the bushveld complex. So just a little bit of geological context. That's a geological map of the bushveld complex. It's the world's largest layered intrusion, a little bit over 2 billion years old. It's a gigantic sill-shaped body, so about 400 kilometers east to west and about the same north to south. That's the Morensky Reef there in red. It's continuous in the two major lobes of the complex. And a stratigraphic equivalent of it called the Platte Reef is also found in the northern lobe. We'll see a bit of that shortly. So this is a sort of schematic of what the Morensky Reef looks like at sort of a what about 50-meter scale. It sits on a major erosional unconformity within the cumulate sequence of the bushveld complex. The base of the Morensky Reef truncates layers underneath it on a scale of a few tens of meters. We're going to look at the reef here where it actually sits on the sidewall of one of these erosional features called a pothole. So, so here's our sample. And on the right, you're looking at a Maia mapper image. This is a three-element red, green, blue image. We've got chromium in red, iron in green, and calcium in blue. These are the major rock types. So from the top down, we've got a pyroxenite unit. This is orthopyroxene here, particular orthopyroxene bronzite, showing here in green. These beautiful little platy grains all piled up like a stack of bricks. And then the spectacular looking orange material here is chromite. These are little tiny chromite crystals that form two separate stringers that in some places actually are in contact with one another. And these two little stringers, these two little chromite seams, are continuous over that entire 400 kilometer width of the Morensky Reef. Nice, extraordinary phenomenon. The bottom of it here, it's a little hard to see in this image, but if you look closely, you can see there's actually a planar layering developed within this anorthosite underneath, and that chromite actually cuts it. So this is actually a pothole where the Morensky Reef layer is eroding the rocks underneath. This anorthosite layer here is actually a little bit of a sort of erosional remnant that's had the low melting components extracted out of it by hot magma flowing over it. And then underneath, we've got this unit here. This is a norite. This is a plagioclase orthopyroxene rock. I should have pointed out this dark blue here is plagioclase. This lighter blue color here is clinopyroxene. And these brighter greens here that we're going to see a little bit more of in a second are sulfide. So now I'm just flipping that on its side, just so we can see a little bit more of it in more detail. And what I want to show you here is just one really interesting finding that came out of the Maia mapper that I don't think we could have found any other way. And that's the exact relationship of the platinum minerals, where the platinum is actually sitting in relation to the sulfides. So this green phase here, which I'm just highlighting now in pink, this is magmatic sulfide. So these are little droplets of immiscible magmatic sulfide liquid that have accumulated with the silicate and oxide minerals at the floor of the bushveld magma chamber. And you can see that a lot of them are sitting here in the reef layer itself, in between these two chromite stringers. There's a little bit of it up here in the bottom of this pyroxenite layer that fairly quickly disappears as you go up into the pyroxenite. And also you can see there's some more of it sitting down here I'll just flick back and forth, you can see it easily. Sitting down here in this mushy anorthosite layer. So what's happened here is this sulfide liquid is molten while the silicate rock was solidifying, and that sulfide liquid actually percolated through the pore space down into this anorthosite mush. But what you notice when we look at this carefully, we looked at quite a lot of samples that show this, it comes to a dead stop when it hits this norite layer. So what that tells you is at the time these rocks were forming, this norite layer was completely solid. This layer was mushy, and then these layers were also mushy and solidifying. Okay, now here's the punchline. Here's where the platinum is. So the platinum is here in the yellow phase, and I'll just flick back and forth a little bit so you can see how it relates. So what you'll notice is that essentially wherever there is sulfide, on the scale of about a sort of a half a centimeter or thereabouts, you also find platinum. Platinum yellow, sulfide in. But the platinum is not actually sitting directly inside the sulfide. This is really interesting because the standard model for the formation of these kinds of deposits is that the platinum is scavenged by the sulfide liquid. The sulfide liquid collects the platinum group elements out of the magma and then accumulates on the floor by whatever. The whole range of models of how this might happen. But the interesting thing is that while the platinum is very clearly associated with the sulfide, it's not actually sitting directly in immediate association with the sulfide. There are many possible explanations for this, but what I think is the most likely one is that a lot of the sulfide that actually accumulated, particularly with the chromite, actually dissolved again, and just left the platinum group behind. That's too complicated a story to go into in 5 minutes, but if anybody's interested, I'm happy to discuss it a bit further. So, but really, for the purposes of this talk, the real point I wanted to make is that nobody ever really noticed this before. And the reason is that normally when people look at platinum in these kinds of deposits, they're looking at thin sections. So that's a typical thin section. So depending on where you put that thin section, that particular one, you wouldn't find any platinum minerals at all. If you put it somewhere else, you might find lots. But the sampling scale of a thin section really isn't adequate to understand the statistical distribution of platinum in these rocks. And you can apply it to exactly the same conclusion to gold deposits, exactly the same issue. At the scale we're typically used to looking at them, you can't really see the spatial relations at the scale which is actually important to the origin of the ore body. So if you take away one message, that's the one I'd like you to get. So just generally summarizing what we can see here, the platinum mineralizations for the platinum distribution, it's very closely tied to the distribution of the sulfide. It's not exactly coincident. In fact, interestingly, there's a much lower proportion of platinum group metals to sulfide in the pyroxenite above the reef. So as soon as you go above that upper chromite, this sulfide actually is much lower in platinum group metals than this sulfide down here. And that's got some really interesting implications as well for the origin of the ore body. And then finally, this point, the platinum group metals and the sulfide percolating into this mushy floor underneath the bottom chromite. Now, it's also very significant for the genetic models. I'll just show you one other thing. This is from a paper that's currently in preparation on these rocks. A couple of colleagues of mine at Cardiff University. This is the basal chromite, so we're just blowing up this little contact down here. I should point out also we actually scanned both sides of the slab. It gives you a really interesting insight into the lateral variability. So even though this layer is so remarkably consistent over such a huge distance, it actually varies quite a lot at short range internally. But one of the interesting things, these are chromite grains down at the bottom here, and you can see they've got these really characteristically strange kind of wormy shapes. You can have all sorts of fun spotting animal shapes in these chromites. But we know because we've actually done some EBSD on these rocks a few years ago. Zoya Rachmanovich, former student of mine. These things actually turn out to be single crystals. So all of these big sort of wormy things are just crystallographic individual single crystals of spinel. Now, spinel doesn't normally grow that way. The only way it grows that way is if it's growing as dendrites. In other words, it's growing rapidly from a supercooled magma. So that's another really interesting insight that comes out of looking at these rocks. Just one final thing I'm going to show you before I wrap up. I'm going to skip now to the Platte Reef. Now, the Platte Reef is considered by most people who work on it nowadays to be the lateral equivalent to the Merensky Reef in the northern limb of the Bushveld complex. But it occurs where the Merensky Reef is actually sitting right at the bottom of the magma chamber. So in this case, the Platte Reef is actually sitting right along the basal contact of the Bushveld complex. And in some places, it actually appears to develop as a series of small sills. So this is another chrome iron calcium map. You notice here this the Platte Reef actually contains very little chromite in this particular place. Sometimes it has more, but here it doesn't have very much. The sulfide again are these bright greeny phases. This sort of greeny orange stuff here is orthopyroxene again that we saw in the last sample. Now what I've done here is I've stretched out the color scale on the chromium, so you're actually seeing very delicate variations, very delicate variability at the scale of individual crystals in the chrome content. And in fact, the edges of these orthopyroxenes are richer in chromium than the pores. And that's exactly the opposite of what you normally find. And chromium is a very compatible element. That's to say, chromium really likes being in orthopyroxene. So the first pyroxene that grows typically has chromium-rich pores and chromium-poor rings. In the flat reef, we quite consistently find exactly the opposite. Now, interestingly, this is something that we've also found. Some work we've been doing at CSIRO with Louis Schoneveld, postdoc work. But in a lot of small intrusions of post-magmatic nickel sulfide deposits, they also show this phenomenon. They also show this unusual, strange reverse zoning in pyroxene. And we don't really know what's causing it, but there does seem to be some sort of empirical association between magmatic sulfide deposits and this particular feature. So perhaps this is a useful exploration guide. Perhaps if we find these kinds of patterns in small intrusions that we perhaps just only got a handful of samples of from regional drilling programs or sparse outflows or whatever, we can use this as a prospectivity indicator. And that's something we've actually suggested in a paper that we've got in press at the moment. If anybody's interested, drop me a line or contact me on Twitter. That's my Twitter handle down there on the bottom, and we'll be happy to pass a bit more information on to you. So that's sort of it from me, and that's just about the end of the story. Just putting this one back that Mark showed you a little bit earlier on, just to show you if you're interested in doing some work with us using this remarkable piece of kit. Those are roughly the sort of costs that we're looking at for big samples. For this particular set of circumstances, not every job requires samples this big, and not every job requires dwell times that long. So there's a fair bit of flexibility to talk to us and discuss it. Then I will just leave you by letting you know we've got another one of these CSIRO webinars coming up. The next one features a talk on regolith and exploration through cover by Walid Salama. So if you want to know a little bit more about that, drop us a line, get on our mailing list. We'll let you know about all of these as they come up. So I'm just going to go to my favorite image and sign off there. Thank you very much.